Section 1 Introduction. Let's start by discussing the challenges and costs associated with large language models, LLMs. These models require a significant amount of computational power and energy for both training and inference. The training costs are mainly determined by the model's size and the amount of data it processes during training. Some of the most advanced models have tens of billions of parameters and are trained on trillions of tokens. The inference costs, on the other hand, depend on the model's size and the number of user queries it handles over its lifetime. This can be substantial, with popular models handling billions of tokens per day. So, the question is, how can we minimize the cost of producing and maintaining a high-quality model? Previous research has focused on finding scaling laws, which are empirical formulas that estimate how changes in model size and training data size affect the model's quality. One of the most influential works in this area found that to scale language models most efficiently, the number of parameters and tokens should grow at approximately the same rate. This scaling law was applied to train a model called Chinchilla, which has 70 billion parameters and outperforms larger, more expensive models, including GPT-3. However, the Chinchilla scaling laws only account for the computational costs of training, not inference. In contrast, the Llama and Llama 2 models were trained on 1 to 2 trillion tokens, which is much more data than the Chinchilla scaling laws would consider optimal. Since inference costs are lower for smaller models, the extra computational power required to train a Llama-style model over a Chinchilla-style model of equivalent quality is justified if there are enough inference requests. Previous work has discussed this trade-off between training and inference computational costs. In this paper, we modify the Chinchilla scaling laws to account for inference costs. We calculate the optimal number of parameters and training tokens, in terms of both computational and dollar costs, to train and deploy a model of any given quality and inference demand. Our calculations suggest that if a large language model is expected to handle a significant demand, around 1 billion inference requests, it would be more efficient to train models that are substantially smaller and longer than those considered optimal by the Chinchilla scaling laws. Next, we discuss computational optimality. Our goal is to minimize the computational costs of a model of a given quality and inference demand. We use pre-training cross-entropy loss as a measure of quality, and floating point operations, flops, as our unit of computational cost. We model our pre-training loss in terms of the number of parameters and pre-training tokens, according to the Chinchilla paper's third scaling law. We are interested in minimizing the sum of our training and inference flops, given a certain pre-training loss. We use the standard approximation of flops for transformer models with a certain number of parameters, 6 times the number of parameters per training token and 2 times the number of parameters per inference token. Our objective is to fix pre-training loss and find the optimal number of parameters and pre-training tokens that minimize computational costs. Our total computational cost depends on the inference demand over the lifetime of the model, but our model's parameter count and data size are determined prior to training. Thus, our analysis assumes that large language model practitioners can estimate their inference demand prior to training. Without inference, the optimization problem can be solved analytically. However, when accounting for inference, determining the optimal number of parameters and pre-training tokens analytically is intractable. Instead, we computationally solve for these values across a range of pre-training loss and inference demand values using the Newton root finding method. Our results show that when inference usage is significantly less than the number of pre-training tokens, Chinchilla models are essentially compute optimal. However, as demand increases, inference costs become a significant factor. For a model with the quality of a 7 billion parameter Chinchilla model and an inference demand of 100 billion tokens, our formula suggests the most computationally efficient method is to train a 6 billion parameter model on 1.18 times the original data. For higher quality models, the volume of inference demand required to shift the scaling law increases. For example, a developer expecting a 30 billion parameter Chinchilla quality model to handle 10 trillion tokens during inference can reduce their total flops by 28% by training a 13.6 billion parameter model on 2.84 times the data. Section Summary. Large language models, LLMs, have high training and inference costs, with training costs determined by model size and data volume, and inference costs determined by model size and user query volume. Previous research has focused on scaling laws to minimize training costs, but the Chinchilla scaling laws only consider computational costs and not inference costs. In this paper, the authors modify the Chinchilla scaling laws to account for inference costs and calculate the optimal parameter and training token counts to minimize compute and dollar costs for training and deploying a high-quality model. Section 3. Estimating real-world cost optimality. We're going to discuss how we can estimate the real-world cost of optimizing a model, specifically focusing on the drawbacks of only optimizing for the minimum number of floating-point operations, flops. The analysis we provided in Section 2 has its limitations when applied to real-world scenarios. In reality, the cost of processing a 3D token request during inference is usually different from the cost of training on D tokens. For example, the hardware utilization during inference can be much lower than during training. This is because small batch size computations can lead to low model flops utilization, MFU, which can be as low as about 1% for inference, but is typically 40 to 60% during training. The utilization also varies between input tokens and output tokens. Input tokens, or prompts, are usually processed in a single forward pass, so their utilization is typically close to training levels. However, output tokens have to be produced sequentially, which can result in low utilization due to memory bandwidth constraints. Another factor to consider is that inference operations can sometimes be cheaper than training flops. This is because models can be quantized before inference, which means converting 16 or 32-bit floating-point operations into 4 or 8-bit integer operations. These integer operations run more efficiently on the same hardware. Quantization can also allow large language models, LLMs, to fit on GPUs with less VRAM, meaning that training and inference may happen on different hardware. To estimate the real-world cost of inference, we need to modify our equation to account for hardware utilization. We introduce three new parameters: training MFU, inference input MFU, and inference output MFU. We also add parameters for training and inference cost per flop. Our new goal is to find the optimal number of tokens and the optimal training size that minimize the sum of the cost of training flops and the cost of inference flops for both input and output tokens. We use approximations for flops for transformer models to simplify this equation. The simplified equation is a model of real-world costs, but it does not consider latency requirements and assumes that MFU and cost per flop do not depend on model size, configuration, or sequence length. However, it is flexible enough to account for different hardware utilization and costs. We show in a figure how models optimized for inference-adjusted cost compared to Chinchilla-style models, assuming typical training and inference hardware costs and MFU. For a model of Chinchilla quality with 30 billion parameters, practitioners expecting 1.5 billion inference requests can reduce costs by 17% by training a 16 billion parameter model on 3.35 trillion tokens. When we compare our compute optimal analysis to our real-world cost analysis, we find that for the same inference demand of 2 trillion tokens, a Chinchilla-70 billion parameter model requires only 1.3% extra flops compared to an equal quality compute optimal model, but costs 36% more than a cost optimal model. This difference is due to the 50 times lower MFU of each inference output token compared to training, which our flop-based analysis fails to capture.